All right, so let's see. So this is the extinction event that happened. And by the way, there were other extinction events. We can't attribute all of them to the dinosaurs, or sorry, to asteroids, but certainly the one that took out the dinosaurs, um, and then led to the rise of man. Oh, see, look, it's right there. The rise of mammals. That's what this is the age of mammals, since the last 65 million years. Um, all right. Anyhow, mass extinctions could have occurred before and after, but many have been related to volcanic eruptions or huge changes in the sea level. All right. So just to um, let you know. Um, all right. So this is the Yucatan Peninsula, part of Mexico. Um, it's really off the coast of Mexico. This you can kind of see the um, using infrared images. You can see where the impact was, and you see most of it. You can it's underneath the ocean. All right. Um, the tail of evolution. Let's see. So as comets approach the sun, the nucleus warms and gas begins to sublimate. It goes directly from that's a better way to describe it. It goes directly from a solid to a gas. The coma forms around the nucleus, and that's when the comet is about 3 astronomical units from the sun. The tail begins to form, and it usually starts to form about anywhere between two and 1 astronomical unit. But the pressure from the sun, from just the light of the sun, pushes the tail away from from the direction of the sun. So the tail always points away from the sun. When the comet passes around the sun, the tail still points away from the sun, which means it'll tend to point ahead of the comet's motion, which is really strange to look at. By the way, when you know where the comet's moving, and it's going in the direction that the tail is, because you normally think of the tail as behind it. Um, Anyhow, solar heating diminishes, and the coma and the tail tend to disappear when it gets anywhere between 4 and 6 astronomical units. So most of the comets um, will spend a great deal of time either out in the Kuiper Belt if they're short period, or all the way out to the Oort cloud, which, as it says there are literally trillions of objects. Not all of them certainly become comets, but something disturbs their their orbit that has been going on for 2.5 billion years, and they will fall in towards the sun. Some of them, by the way, just go crash right into the sun, and that's it. All right, so that's the chapter. That's chapter 10. Um, let me um, let me pause this. All right, so I'm going to do some of these problems in our problem set. So these are from chapters 9, 10, and 11. All right, so the first one here says, how long does it take in hours? Okay, so we want to know. So right away, when you start reading this kind of stuff, look what are we looking? Oops, switch that to pen. What we're looking for is the yeah. I didn't change the size of this thing. Okay, there we go. What we're looking for is the time in some number of hours. All right, so that's really what we're. All right, see the average distance from the Sun and Pluto is 39 AU, and 1 AU is 150 million kilometers. All right, and then the distance to Uranus is 19.8. And so there's basically two questions. Um, how long does it take light or any form of electromagnetic radiation, right? All of them travel at the speed of light. So we have so there's in the formula sheet the formula sheet has c, which is the speed of light, is equal to distance divided by time. But see, you can rearrange that equation and solve for time, which is on the formula sheet as well. All right, so it looks like this. Of course, time is equal to distance divided by the speed of light. Right? And so, if you know the distance in meter, or sorry, in we'll do it in kilometers, right? So just to remind ourselves, c, and this is on the formula sheet as well, is 3 times 10 to the 5th kilometers per second. All right, so we're going to use that when we do this. All right, so what is D? All right, so in part A, let's do this. So for part A, we'll do both of them for goodness sakes. For part A, it's going to be 39.5, right? 39.5, but that's of course in astronomical units, AU. But we know that in 1 AU, there are 150 million kilometers. 150 times 10 to the 6th, which is million, kilometers. All right, so right away, the AU's cancel, and so that would be the number of kilometers, right? So when you multiply those two things, and then you just divide by the speed of light, right? And that'll give us. So look, here's what this is going to be. It's going to be divided by 3. 3 times 10 to the 5th, and that's of course kilometers per second. So see, now what's going to happen is the kilometers will cancel, and so it gives us an answer in seconds. And so some number of seconds. All right, so let's figure that out. Let's figure out how many seconds. All right, so let me get my calculator right here. We've got all the numbers to do this. Here, let me move that over here. All right, so the first thing I'm gonna do the first part. So 39.5. That's point. I'm messing up here. Sorry, 39.5 times 150 million. All right, so times 150. You either hit the EE button or the EXP button to the 6th. All right, so that's going to be the distance, right? In this equation, this is the distance divided by the speed of light. So this is the distance, and then you divide it by 3 times 10 to the 5th. So divided by 3 times 10 to the 5th. Remember, this comes out because we have seconds down here. That'll come out as an answer in seconds, right? But we can convert that to here. I'll show you that in just a second. So this is what it equals. So it's 19,750 seconds, right? So that's the number that goes here. 19,750 seconds. All right, and then what you can do is let me get a little bit of room. Well, here I can do it right here. All right, so if you have that number of seconds, we know so 19. I should have just written it right there. 50 seconds. This is a separate problem now, and we just say, all right, well there are 60 seconds in 1 minute. All right. And then we just say, well, there are 60 minutes in 1 hour. Right? And that's it. Like you see, in other words, the seconds cancel, the minutes cancel, and so you just take this number and divide by 60 squared. and that'll give you the number of hours. And you'll see why we did it in hours. It makes more sense. All right, so then we divide by 60, and well, it's really 60 squared. Divide by 60 squared. All right, and that is going to equal. All right, so I think it says to round to final answer to one place past the decimal. So this one, the answer would be 5.5 hours. All right, so that's the answer to A. It'd be 5.5 hours. All right, and we'll quickly do the one for B as well. It's exactly the same thing, but now we have 19.8 astronomical units. All right, so here we'll set this problem up again. I'll just try to do it all on the calculator. I mean, it's exactly the same as this. Instead of the 13.5, it's going to be 19.8. All right, so there we go. And of course, it's going to take less time. It's 5.5 hours to get to Pluto. Uranus is closer. So. All right, so let's clear that. Let's see, what was it again? Oh yeah, 19.8. All right, so times what one astronomical unit is, 150 times 10 to the 6th. All right, so that's the distance that it travels divided by the speed of light, 3 times 10 to the 5th. We're using 3 times 10 to the 5th because that was the numerator was already in kilometers. So look, you can see it's already less. It's only 9,900 seconds, and then we divide that by 60, and then we divide by 60 again. So in other words, we divide by 60 squared. And so it only takes light or any form of electromagnetic radiation, visible light, gamma rays, radio waves, any of it, they all travel at the speed of light. So to get to, the average distance to Uranus, it would only take 2.75 hours. So part B, so this is for part B, is 2.75 hours. And if they wanted you to round it to one place past the decimal, that would be 2.8 hours. All right, so let's, very nice. Here, let's work on another one. So here's what it says. At its closest, this is the second problem. At its closest approach, Jupiter is about 4.2 astronomical units from Earth. If the planet is 140,000 kilometers in diameter, what is its angular size as seen from Earth in arc seconds? Okay, that's important to remember that that's going to be in arc seconds. All right, so I'm going to write out the equation. All right, so anyhow, you can of course find the equation on the formula sheet. All right, so it's really just this angular size equation rearranged, which is on the formula sheet. You don't have to rearrange it yourself; it's already been done. So alpha is equal to 180 over pi, the actual size of the object, which is L, divided by the distance to the object, which is D. Now, L and D have to be in the same units, and alpha will turn out to be in degrees. All right, so to get the same units, you just have to say, so it's 4.2, AU, but of course we have to change that, and there are 150 million times 10 to the 6th kilometers in 1 AU. All right, so the AUs cancel, the kilometers cancel, and that's, plug in the numbers, and then we'll have it. But the answer will be in degrees. We're going to convert it to arc seconds by dividing it, or by multiplying by 60 squared. So I put all this in the calculator. Alpha turns out to be 0.0127, and that's of course degrees, to put it in arc seconds, all I had to do was multiply by 60 squared.